Now let's look at this question associated with the Kaplan-Meier estimate calculation. A certain profession admits new members to the status of students. Students may qualify as fellows by passing a series of examinations. Normally, student members sit the examination while working. There are two sessions of exam. Employer provides study support. Access the cost of providing this study support. That's where we are trying to find the average time for the student to qualify. Okay, there are 23 students for the first exam 2003 and included the last session of 2009. So probably it's like almost 14 sessions have been tracked till now. Right, the students entered in 2003 and they have come out of 2009. So there are 14 sessions that have been tracked. The following data records the number of sessions which have been held before the event occurred for the student in this cohort. So there are sometimes people there is one student who have qualified within 6 sessions, a couple of them within 8, few of them within 9, 11, 13. And we also have the examples of students who have left the study, some of them, one of them in the fourth session, or probably one in fifth, one in eighth, and something like that. And so how many of them got qualified? 6, 8, 11 of them have qualified till now. 5 of them stopped studying, so 16, which means 7 of them are still studying even at the end of 2009. So they are continuing their studies even at the end of 2009. Now, we are under the requirement of computing the survival function wherein we have treated qualifying as the hazard. In general, we talk about this being in our typical mortality examples, we see that this being the death and this being the censored kind of a data. They have stopped studying for various other reasons. So this is typically the censored kind of a data, whereas the topper one is the death, and we are trying to find out the survival function which is associated with the hazard of getting qualified. And T is the number of sessions since 1st Jan 2003. So going with the Kaplan-Meier estimate model, I am looking at the T. Okay, the first, when I am looking at zero period, fair enough. In the zero period, I had around 23 students, so NJ is around 23, and the number of students who qualified by that time, D. Here it's like a hazard because it's a hazard function. I am looking at it as a D, where 0 students have typically got qualified, and during this period before the arriving of the 6 itself, the number of people who got censored is 2 during this period. 2 of them got censored because the timelines I am looking at is 0, 6, then we had 8, then we have 9, then few people qualified at 11 and few at 13. So between 0 and 6, 2 of them got censored because we have seen people stopping studying at 4 and 5. So the C is 2, which is leaving me that whatever the hazard rate that I have to compute, right, the hazard rate which I generally represented by D by N. For each of the period, the hazard rate I can represent it as the number of deaths or number of qualified to the number of people who are available. So in this case, I can take it as 0 divided by 23, and which means the 1 minus hazard rate, which is more like a survival function. So the survival rate for that particular period is 1 minus of D by N. The same logic I can take it to all. By this period, only 21 people are available. Out of them, how many got qualified at 6? Only one person got qualified. And between 6 and 8, no person has left. So the number of lefts are 0. So the hazard rate will come out as 1 divided by 21. That is the hazard rate, and that is operating out. If I have to take the survival rate, I am taking it as 1 minus the hazard rate. Similarly, at 8, how many participants are left? The number of participants that are left is 21 minus 1 minus 0. 20 of them are left. Out of them, 2 of them qualified. So I'll take 2. What about survived between 8 and 9? Only one of them moved out. So the censored is 1, which will give me my hazard rate again as 2 divided by 20, giving me a 0.1. And of course, the survival rate is 1 minus 0.1, giving me 0.9. And the same logic holds true for 9. The number of people who are left are 20 minus 2 minus 1. These are the number of participants left. Out of them, in 9, 2 or 3 of them got qualified, and there is no one who has got censored. So which is resulting in a hazard rate for me as 3 divided by 17, and 1 minus the hazard rate works out to 82. The same logic for year 11, for the session number 11, the number of participants who are left are 14, and at 11 there are 2 people who got qualified, and the number of people who got censored between 11 and 13 is only 1. So I'm getting this to be my hazard rate and this to be the survival rate. And for about finally, the last one being the number of people who are left are 14 minus 2 minus 1. 11 people are left. And out of these 11, in the 13th session, 3 of them got qualified, but none of them got censored. So these are the typical numbers that are existing, and from here the multiplication of all these survival function is what is my Kaplan-Meier estimate. Kaplan-Meier estimate of the survival function for me is a simple product of all these numbers. I am multiplying all these 5, 6 to give me the Kaplan-Meier estimate. Right, to give me the Kaplan-Meier estimate, let's say at the end of the 7 sessions, if I want, there is a 44% probability that a person who has started the exams in session 1, the probability that he still doesn't get qualified by the end of session 14 also is around 44%. That is what we are bringing out as the probability of survival. So that's the typical way we can operate. And probably individually also, if I have to know the survival, the probability that a person who started in the beginning, he is surviving up to 6, means the probability that he does not get qualified even at the end of the 6 sessions is 95%. The probability that he does not get qualified even by 8 sessions is around 85%. The probability that he does not get qualified by 9 sessions is 70%. The probability that he does not get qualified even by 11 sessions is around 60%. And the probability that he does not get qualified even after the 13 sessions is around 44%. 13 plus kind of sessions also, the probability that he does not get qualified. So between 6 to 8, the probability is around 9.95. Between 8 to A 9 it is around 85%. That's the way we can typically work it out. That is how we compute the survival function using the Kaplan-Meier estimate. Alright. Now let's look at a numerical concerning the Kaplan-Meier estimate again. This is again involved in terms of calculating the survival function. We know that Kaplan-Meier estimate as well as Nelson-Allen estimate, both of these are the measures to compute the survival function. So now we'll take again some data set to try to understand this Kaplan-Meier estimate and even getting to a layer of computing the probabilities from probability of survival or probability of death from this Kaplan-Meier estimate. Okay, at Miracle Cure Hospital, a pioneering new surgery was tested to replace human lungs with synthetic implant. Operations were carried out throughout June 2010. Patients who underwent the surgery were monitored daily until August 2010. So it's almost they were monitored for a 3 month kind of a period. Let's say the date of surgeries were given and the date of leaving the observation, or probably whosoever have died, they have been classified as died, and whosoever have just left the hospital until they died, or they left the hospital, whichever was sooner, results were shown. When no data is given, the patient was alive and still in the hospital at the end of August. So what we are trying to look at here is there are almost 14 patients who were observed, and their dates of surgeries were specified and date of leaving the observation, because either they were died during the observation period, or they left the hospital intermediately without completing the course, or even they might have completed the course but they were not necessary to be kept in the hospital. But wherever there were blanks, it's an indication that they completed the surgery, they did not leave the hospital, and they were alive until that particular period. Now, before we do some kind of an estimate in that particular example, if I look at this particular question, explain whether each of the following types of censoring is present, and for those present, explain where they occur. When I look at right censoring, yes, right censoring is present, because by the time these people they left, they were alive, and they did not leave the hospital also. So I cannot I don't know how long will they be alive. How long will they be alive? I'm not sure, which means I cannot assess if a person who was alive for, let's say, 2 months after the surgery, for how long they are going to alive. So that is why we are calling it as right censoring, because we have censored those observations after a specific time period. We are not going to observe any more those observations, so we cannot get an assessment relating to their deaths anymore after the time period. So wherever we have a fixed time period, we are bringing in the right censoring. And so all those people who have left while being still alive, these kind of people, right? We don't know, we can't assess anything about their time period of survival. And even those people who have left, all these people, there is some kind of a right censoring. And left censoring wise, I don't think anything is there, because the exact dates of surgery were given. Rather than this exact date of surgery, probably if we had information just about a month of surgery or something, then probably we could think of a left censoring being present. And regarding the informative censoring, whosoever have left, probably I see there is some amount of informative censoring present in the data, because all those people who were left in the middle, who left the hospital in the middle, I could assess that there is I can be very strong about the information about them, saying their health has improved drastically. I can very well feel that that their health has improved drastically, and that's one of the prime reasons they might have left the hospital, right? So compared to the others who are still in the hospital and are getting monitored, these people might have recovered much quickly, and that's the reason they have left the hospital and then the under the observation area also. So because there is some kind of an information that I could derive confidently about those people who were censored, I say there is some kind of information based censoring that is present in the data, right? So that is how I define the different forms of censoring. Now the next question which I am interested in looking at is calculate the Kaplan-Meier estimate of the survival function for these patients, stating all the assumptions. So this is where I need to compute the Kaplan-Meier estimate of the survival function. Right, we'll calculate the Kaplan-Meier estimate of the survival function. So for that, let me make a quick note down of the time periods. All right. So I'll make a note of the various patients A, B, C, D, E, F, G, H, I, J, K, L, M, and N. I made a note of all the patients. The date of surgeries, I can make a note of them. I can make a note of their date of surgeries. 1st June, then 3rd June, 5th June, 8th June, 9, 12, 16, 17, 22, 24, 25, 26, 29, and 30. Okay, these were the dates on which the surgery was performed. Then we are talking of date of leaving. Date of leaving the observation. So A has left on 3rd June. B has left on 2nd July. C, D did not leave. E left on 11th July. Then F did not leave. G left on June 21. H on 12th August. I did not leave. J on 29th June. K on 20th August. Right. L did not leave. M on 6th August. 1. Then reason for leaving. Whosoever have left, died and left. So the first one has died, the second one has just left the hospital, and about E and G, both of them have died, whereas H has left and the next two have died, whereas the last one has left. Now based on this, I can very well work out the duration. For those who did not leave, I can take 31st August as their date of ending the observation, because we have monitored them only until 31st August. Alright, we have observed them only until 31st August, so they were simply censored. Now I am looking at the durations for each of them. I'm just taking the difference between the date left versus the date of surgery, giving me across that these are the different durations that are associated with the different lives. Right, these are the durations that are associated with the different lives. So this will help me. So from this data, I could very well get into the Kaplan-Meier estimation mechanism. Only for those died, I will take it in the serial order. So I'll take Tj, which is the timing from the deaths. Initially, I start with a 0, then a 2, then we have a 32, then we have a 5. So I'll take 5, and there is one more 5. So there are two people who have died within 5 days, right? One has died at 32, one at 56. So overall there are 5 died, one at 2, 2 at 5. Then I have one at 32 and the other one at 56. These are the people who have died. So what I am more interested in is the number available at that point in time. NJ, I had 14 people who were alive at time 0, but at time 2 I had again 14, but at time 5 only the first person A has died, less all are available, so I had 13 people. But at time 32, if I have to look at time 32, the first 1, 2, 3 and 4 are not there. So which means I am left with 10 of them, and probably at time 56 along with those 4, even this person is not available, 5, and even this person is not available, 6. So 6 of them are not available, which means the number available before the death is 8. So at this point, if I am looking at the number of deaths at here it is 0. Probably if I am looking at 2, there is 1 death. At 5 there are 2 deaths, and then at 32 there is 1, and 56 there is 1 death. Similarly, when I am working out for number of censored before the period, between 0 and 2 there was no one who was censored, and same way between 2 and 5 there was no one who was censored, but between 5 and 32 there was one who was censored at 29, and similarly between 32 and 56 there was one who was censored at 38, and finally the 7 who were censored at the end of the observation period. So based on this I can find out the hazard. I can find out the hazard function lambda, which we have written it as dj by nj. So here I can find out the hazard function dj by nj for each of these periods. So these are the numbers that are working out to dj by nj. And now we know the Kaplan-Meier estimate. For that I need 1 minus the hazard function to each of them. So I'll take it as 1 minus the hazard function at each level, working out to this. And from here we are talking about the survival function s of t, which is nothing but the multiplication aspect. So here I am taking this number, I am multiplying it with this number. So I am getting the survival function for each of the period. This is a survival function between 0 to 2, right? 0 to 2 period survival. This is between 2 to 5, and this is between 5 to 32. This is the survival function. 32 to 56. This is the survival function, and 56 to how many days are there completely? 92 days. 56 to 92, this is working out to be the survival function. So these are the survival functions at each of the layers, right? So I have the Kaplan-Meier estimates for each of the age ranges. So from 0 to 32, this is what is the survival function and something like this, which means now I can very well go ahead in terms of plotting for up till 0. So for each of the layers, I can think of plotting a kind of see, I could take 0 to 2. If I plot a kind of a histogram, I will get a very good clarity in terms of for each of them what is the typical survival function. So a simple graph can be plotted by taking a kind of a area on the x-axis, so like 0 2, then probably 5, then probably 32, 56, like this. From 0 to 2 it is 1 survival function, then there is a small dip 0.9, then again there is a dip point. So this is the way the typical survival function works out in case of a Kaplan-Meier estimate. Now, so that is what is a suitably labeled graph, fair enough. Now estimate the probability that a patient will die within 4 weeks of surgery. 4 weeks of surgery is coming out to 28 days. Let's look at what is the survival function for 28 days. This is the survival function for 28 days. Because we are talking of this is the survival function for 5 to 32 days. So we are looking at it for 28 days. So which is working out to this being the survival function, which means the probability that the person will die within the 28 days, within 4 weeks of surgery is 1 minus this, saying around 21.42% chance. The probability is around 21.42% that a patient will die within 4 weeks of surgery. So this is how we can use the Kaplan-Meier estimate calculation for assessing the survival function. Alright. This is a slightly interesting question relating to Nelson-Allen estimate, because we have the survival function here, and based on the survival function we have to work backwards in terms of computing the number of deaths as well as number of them who got censored. In general, for the calculations which we get into, we first have the information relating to the deaths and the number of records that were censored, and based on that we can typically compute the Nelson-Allen estimate of the survival function. But now in this case we have the survival function with us and we have to work backwards, so slightly making it as an interesting numerical to work out. Just go through the content of it. A researcher is reviewing a study published in a medical journal into survival after a certain major operation. The following 16 patients from the point of surgery. So 16 patients are studied from the point of surgery perspective, and the patients were studied until at least 5 years after the surgery. And either that's an end of the study, or even in between somewhere the patient could have been withdrawn from the study as well. And after all those things that have been done, we are seeing that these are the survival numbers that are available with us. Okay, the duration since the operation, we'll take up duration since operation and the survival function S of t. So here it is saying 0 less than or equal to 0 less than or equal to t less than 1, between 0 and 1 year. So probably otherwise let me write it as between 0 to 1 the survival function was 1, means no one died between 0 and 1. But from 1 to 3, 1 to 3, the survival function came to 0.9355. Similarly, from 3 to 4, the survival function came out to 0.7122. This is as per the Nelson-Allen estimate. And between 4 to 5, the survival function came to 0.6285. Using this, we are supposed to work out. Okay. Now, before we go ahead with our workout, the question was typically asking us what are the types of censoring that are present in the study. One, by straightforwardness, we have right censoring that is present in the data, because at the end of 5 years, we are stopping the observation. At the end of 5 years, we are stopping the observation, means we are not observing the survival of the people. We are not observing the survival of the people or the after the 5-year period. So wherever I'm stopping the investigation after a certain point in time, we are talking of a right censoring present, and along with that I could also see a kind of a random censoring present, because the people who have left the study, assuming that at least some of them might have left the study, there is no clue at the time point at which they are leaving the study. So there is a lot of randomness in the people who have left the study. So there is some amount of random censoring that is present in the data. So that is one aspect. So typically I observe these two important forms of censoring that are present in the data. And before we proceed with our numerical, we are very much clear that the survival function that comes out in case of the Nelson-Allen estimate is purely a function of e to the power of minus the hazard function lambda t, wherein the way we are computing this lambda is nothing but the way we have computed the lambda in case of the hazard, in case of Nelson-Allen estimate, is basically the number of deaths divided by the number of people who were alive at that particular point in time, and we have been adding up the stuff. So this is what we were using for computing the survival function. So what I see really look at is, from the survival function, it's better that I compute the hazard rate first, so that I can use it quite comfortably. So from the survival, I can find out the lambda, which is the hazard rate, which is, you could see here, if I am looking at survival function, s of t is e power minus lambda t. Minus lambda t is going to be arrived using the log survival function, and the hazard rate is nothing but minus log survival function. So I'll do the same. I'll say minus log survival function. So here the hazard rate is 0, and probably as I move further I see the numbers 0.06. So I am getting the hazard rate for each of the period, which is a summation. So if I want it exclusively for the period means I am subtracting the stuff. So between 1 and 3, if I am looking at the hazard rate, it is nothing but it's 0.06. But if I am looking at it between 3 to 4, it is 0.27, and between 4 to 5, it is 0.19. Or probably I can look at it, I can look at it as, so this is coming out to 0.27, whereas this is, let me just make the necessary modification. The hazard rate here is this minus this, and continuing it in the same way, yeah, it is 0.125. Now, what I can very well look at is how can I convert it into DJ, the number of deaths, the total number of patients, and from there I could even try to infer the number who are censored by that time itself. Right, number who are censored by that time itself, I should be able to make out. Now, 0.066 in the form of integers, if I have to establish it, it is as good as 1 by 15, because at the max I can have 16 in the denominator, right? I can have 16 in the denominator because 16 patients were there. So if I am looking at 1 by 16, it is coming out to 0.0625. The first death itself is giving me 0.0625. So I could have really looked at it as 1 by 15, which is almost matching with the number. So which means I could say that during this period there were 15 people only, and out of them one has died. So by this time already one got censored, because only out of 16 we are seeing only 15 at that point in time. So one was died, one was censored. So this leaves me only with 14. For the second period, if I am seeing my ratio out of the 14, I need different combinations of the ratios which could give me 0.27. So if I am looking at 1 by 14, no, it is not. Probably I can look at 2 by 14. It is not matching 0.27. I could see 3 by 14 is also not matching, and even a 4 by 14 it has crossed. So none of them relating to 14 has given me that 0.27. So I'll try it with 13. So probably I can try 2 by 13, not a case. Or probably I can try 3 by 13, no. And what about 4 by 13? It has crossed. So even 13 may not be an option. So I'll try 2 by 12. Even that is not matching. 3 by 12, we know it's 0.25. 4 by 12 is 0.33. So 12 also can't match. Now if I'm looking at with 11, probably I can try 2 by 11, 0.18. And I could try 3 by 11, which could give me 0.2727, more or less matching, which means by this period there are only 11 participants, 11 observations that are there, and I can say 3 have died during this particular period, which means 3 have already got censored during this point in time. During this point in time, 3 of them have already left the observation, because we had a total of 14 people, and of course 3 of them have left the observation before this particular point itself. So that are the number of censored during this period. Now at the max I have 8 people. Out of 11, 3 died during that period. So at the max I have 8 people, and here I need to generate 0.125. So it's almost matching with 1 by 8. So which means here I had 8, out of which 1 died, and that is what are the numbers. Now this is what has generated from the reverse. I was able to calculate all the deaths, number of observations during each of the period, number of patients who are at risk during each of these period, and finally we are saying that there was 1 death at 1 year duration, 3 deaths at 3 year duration, and 1 death at 4 year duration. So this is how we are ending up doing the computation of the deaths. So which means if 5 of them have died during the period, I could very well see that 11 of them could get censored. Of course, out of them, at least I could be clear that 4 of them got censored before the observation ended itself, and 7 of them got censored till the last. They are waited for 5 years, and there were no deaths for those 7 patients at the end of even 5-year observation period also. So sometimes with the kind of information that is available with us, we may have to work backwards to try to establish these kind of relationships in terms of estimating the number of deaths and probably number of those who got censored, primarily working backwards from the data. That kind of a comfort level needs to be very much developed. All right.